Pleasure to present our speaker, Professor Gunther Uhlmann. Gunther graduated in 1976, and since then he has held academic position in Harvard, Urban Institute, MIT, University of Washington, and University of California. And this is only to restrict ourselves to this continent. Because if we move a little bit, we will find in the CV that in the last few years we have held quite distinguished visiting position in Paris, Cambridge, England, and in the next few years in Finland. Among Professor Uhlmann Award, one finds the Boucher Prize of the AMS in 2011, the Clayman Prize for the Cyan in 2011. He has been a Sloan and Guggenheim Fellow. He's a highly cited researcher, a plenary speaker of the Applied Mathematics World Congress in 2007, invited speaker in the International Congress of Mathematics in Berlin, and among infinitely many other distinguished. Well, when I was reading Gunther CV, one thing that came to my mind was the idea of the good chicken wine that the quality improves with age. Then Gunther.
Well, thank you very much, Gustavo, for the very kind introduction. I'm very happy that he didn't tell you about many of the embarrassing moments that he knows about. I also would like to thank the organizers for the invitation to give a talk here, and it's a great honor and pleasure for me to do so. Particularly, I am originally from Chile, in spite of my name, and also I work in the US now. So the subject of this talk is about invisibility. Of course, this has fascinated humans for a long time. I assume that everyone in this room has wanted to become invisible at some point or another. Lucas says no. The interest, at least that we know of, has started in the mythology, in the Greeks, Perseus versus Medusa, in the writings of Plato, about the moral impact of becoming invisible. And there has been a lot of things in more recent fiction, so let me show you some clips. It's too loud. Okay, so The Invisible Man, a famous novel of H.G. Wells, and he becomes invisible by changing his index of refraction. So he was a scientist, a chemist, and through a chemical procedure, he makes the index of refraction, which determines how much light is absorbed, scattered, refracts, and so on, the same as of air. And so the rays of light will go straight through. and so he becomes invisible. You can see the clothes here because the clothes have a different index of refraction and they reflect, and so on. So you see through reflection, refraction, scattering, and so on. This is highly not recommended procedure, also not likely to work because the human body is very heterogeneous, scatters, absorbs light and reflects light and so on. Also, the invisible man himself wanted to reverse the process and he couldn't. But however, the idea of changing the index of refraction is a good one. So this is was pointed out to me by my son who likes comics, Susan Stone Richards, the Invisible Woman, you saw the clip. So she becomes invisible by deflecting light around her, by some kind of power, we're not told how. So she deflects light around her, and in that way she becomes invisible. I think it was on the fabulous, the Fantastic Four. And a more scientific version of that is in Star Trek. So Star Trek, the ship makes itself invisible by having a gravitons. So this is the first analogy with general relativity. We know that very strong gravitational field will deflect light. So they have gravitons, we don't know how to get these. But these are, however, the idea is a good one again. So they have very strong magnetic gravitational field, and that will deflect light around the ship and will become invisible. So how are we going to do this? We're going to do this by creating a cloak of invisibility, a la Harry Potter. So we're going to change the index of refraction. We're going to create a cloak that has an index of refraction such that the rays of light will go around the object and whatever is inside is going to be invisible. And this is me half invisible here. You can see Maxwell equations in the background. This is another one. And my hand becoming invisible. So now coming to the scientific ideas of invisibility. So what I'm going to describe is what's called transformation optics in the physics literature. And there were two articles in Science that received a lot of attention in 2006 by Pendry et al. Controlling the electromagnetic fields, and a related article which was a little bit earlier, published in the same issue by Uhlmann, optical conformal mapping, and both of them use transformations, as I'm going to describe later. This is a more general description, and this is in 2 dimensions, using conformal mapping. But the same idea of Pendry et al., in fact, the same transformation was used by Greenleaf, Lazarus, and myself when we were studying Calderon's problems, an inverse problem that I will describe a little bit later, that was published in 2003. And Science magazine has a very good description, and I will try through the talk to explain this. So the ultimate camouflage, so the real breakthrough in line with theoretical tools used to make the clock. In such transformation optics, the searchers imagine a Einstein. Again, there is another analogy with relativity, warping empty space to bend the path of electromagnetic waves. A mathematical transformation then tells them how to mimic the bending by filling and warp space with a material whose optical properties vary from point to point. Any way you look at it, the ideas behind invisibility are likely to cast a long shadow. Of course, we don't want a shadow for invisibility. So this is a cartoon from the paper of Pendry et al. These are the rays of light. And in the ball of radius R1 is Harry Potter, who wants to become invisible. And the blue is the cloak. So the rays of light are going to go around. We're going to build the material here whose optical properties are such that the rays of light will go around, and when you make an observation outside this ball of radius R2, it looks like the rays went straight through, like in the case of the invisible man. So whatever is inside here is invisible. But there is a question of the waves, whether the waves do this. These are the pictures of the rays of light. And in our paper in 2003, we built a conductivity. So the conductivity determines the electrical properties of a material, how much electricity is being conducted. On the left, you have a picture of homogeneous conductivity 1. So the currents, which are the waves in this case, go straight through. So we're going to build a conductivity here such that the currents, very much like in the case of the rays that I showed earlier, go around the object, and when you look on outside this larger ball, it looks like the currents are the same as in the picture on the left. So you cannot distinguish between the picture on the left and the picture on the right, and whatever is in here is invisible to electrical measurements. So so how are we going to do this? We want to deflect light. As already mentioned, in Einstein's theory of relativity, you deflect light by a very strong gravitational field. A dramatic effect of that is what's called gravitational lensing. It's such strong gravitational field that the light makes a lens. And this is used in astronomical observations to see behind very large objects, stars and so on. So you can go around the object and see on the other side. Of course, you have double images or more, or quadruple images and so on. So, but we need a strong gravitational field. What we want to do is something like that, but optically for electromagnetic waves. Another dramatic example of a strong gravitational field is a black hole. So here is the event horizon. So the rays of light are trapped here, and they cannot get out if they go after the event horizon. And so we want to have this effect, but the opposite to this effect. So the rays of light we want to go around, not be trapped here. But also, later on I will talk about creating artificial black holes. So this is what we want to do, an optical white hole, the opposite of a black hole. So the rays of light will go around the object, and when you make the measurements outside, it looks like the rays of light went straight through. So let me describe the theory of light. Light has been of interest to humans also for a long time. The ray theory of light is based on Fermat's principle. So one goes light tries to go from point A to point B in the minimum amount of time possible. So that depends on the index of refraction of the material. Different index of refraction then will have different paths. The straight line here corresponds to the case of index of refraction 1. But the index of refraction is very slow here and increases, then the rays of light will deflect in such a way to form these curves. It will curve, and in fact, for the people who know about this, is the geodesics of sound metric. So the index of refraction and the ray theory of light explains many things that you see. And for instance, you have the air and water have different index of refraction, and the rays of light break. Here, this is another effect. In order to go from this point to that point in the minimum amount of time possible, this is Snell's law. And so you see the fish in a different position than actually is. So that's an illusion. And another optical illusion is a glass of water. Everyone has experienced this. A straw in a glass of water looks like it has broken, but the straw has not broken, it's just an illusion. And invisibility is some form of optical illusion. And the effect I mentioned before, this is a much more difficult to obtain, that the rays of light will curve continuously, not just break, in such a way that bend can be observed in nature, for instance, in the desert, and thus produces a mirage. The index of refraction is such, it's so hot that it's very slow, the index of refraction is very small near the desert and then increases continuously, and so the rays of light will curve, so when you think you're seeing water, you're actually seeing the sky. I'm sure in Mexico here it's very hot, and you have seen many instances of this in the road. You see patches of water, but they are not there. It's just an illusion. Okay, but there is also the question of whether the waves will do the same. And so some of the same authors ask the question of whether full wave clocking, not just for the rays, will be possible, even in theory. And the answer is yes, and I will show you how to do this. So this is based on our work for the waves. So I'm only describing here plane waves coming in. So the waves come in, and then they're deflected. And when you see them on the other side, it looks like they went straight through. So the wave theory of light is summarized by Maxwell equations. This was one of the great syntheses of all time in physics and science, a great discovery, so that summarized the behavior of the electromagnetic field, E and H. Maxwell must have been so elated when he discovered that light actually behaves as an electromagnetic wave. The speed is the speed of light. Amazing discovery. D is electric displacement, B is the magnetic displacement, and the electromagnetic properties of the material are described by the electric permittivity and the magnetic permeability. K here is the frequency, so I'm describing what's called time harmonic waves. And the connection with the index of refraction, and we are going to come back to this later on, is the square root of epsilon times mu. So nowadays, the ray theory of light is interpreted as an approximation, a high-frequency approximation to Maxwell equations. If you want to mention one scientific discovery that has so many technological applications, is Maxwell equations. This was basic theory at the time when they were doing it, and now almost everything is based on Maxwell equations. Light, electricity, television, radio, cellular phones, etc., etc. So behind Maxwell equations, before I go on, there's a lot of geometry, hidden geometry. These are a fascinating set of equations. And one of the important things, and this is what we're going to use, is that if you change coordinates, you use a different reference frame, then the new equation for the electromagnetic field will look exactly of the same type. The epsilon and the mu will change, the E and the H will change, and so on, but they will be of the same type. So we are going to say that the equation is invariant under transformations. So this is a key point for invisibility. In fact, invisibility will be true for any model, any equation that is invariant under changes of coordinate. And epsilon and mu, the electromagnetic parameters, are going to be constructed in such a way that these are matrices. These are what's called anisotropic material. The electric displacement and the magnetic displacement are in a different direction than the electric field and the magnetic field. So these are going to be matrices. So for instance, crystals are very anisotropic in general. The epsilon and the mu are not just scalar functions, are matrices. So as I said, behind the theory of transformation optics is the fact that Maxwell equations are invariant the changes of coordinates, and then we're going to build the cloak so that epsilon is equal to mu. And I'm going to write it this way because this is going to come out again and again and again, is the inverse of a semi-positive definite symmetric matrix. You can think of this as a Riemannian metric for the people who know differential geometry. So the inverse of that times square root of the determinant of G. Okay. So this is going to be the blueprint of what are the properties of the cloak of invisibility. So a similar phenomenon happens for Helmholtz equation that describes acoustic waves and also quantum waves in some sense. So suppose you are decoupling the electromagnetic field, and this is what's called the Laplace-Beltrami operator. And so the Laplace-Beltrami operator in coordinates is written in this way. So this is the square root of the determinant of G times the inverse of G. Again, this quantity here appears again. Square root of the determinant of G times G upper ij. For instance, if this is vacuum, this is the identity, and this is just a standard Laplacian. But the point I want to make is this is another equation. It's a scalar equation in this case. It's invariant the changes of coordinates. It's manifestly so because it's written in geometric terms. So again, this is Helmholtz equation, and what we were considering in the paper I mentioned in 2003 was the static case when the frequency is 0. So E and H are harmonic functions. And this is equivalent in dimension 3 or higher to what's called the Calderon's problem that we were studying, an inverse problem that has been studied a lot in the last 30 years or so. So I'm going to describe that. And the ideas for that, to make things invisible for conductivity, apply to Helmholtz equation and apply to Maxwell equations, and again, to any equation that is invariant the changes of coordinates. So what's Calderon's problem? Calderon's problem is the following inverse problem. So you have the conductivity I mentioned before, and let's assume for the moment this is a scalar function. So this describes electrical properties of the domain. For instance, blood is very conducting, copper is very conducting, that's very beneficial for Chile. So the question is, can you recover the conductivity inside a material by making voltage and current measurement just on the boundary of the material? And this is called Calderon's problem. As you well know, this is famous, another famous Argentinian analyst that proposed this problem in 1980, and he considered it in terms of geophysical prospection, trying to find oil. He worked in the summer of 1949, I believe, for the oil company in Argentina, Yacimientos Petrolíferos Fiscales. And he thought of this problem then, but he didn't publish his results until many years later. And more recently has been proposed as a method for early breast cancer detection because normal breast tissue and cancerous breast tumor have very different conductivities, again, because tumors attract a lot of blood, very highly conducting, so you notice a very high contrast of conductivity. So this is Calderon, very serious, but he played the tango, I believe. And he danced the tango. And he said something very interesting when he accepted the doctor honoris causa of the Universidad Autónoma de Madrid. This is my translation. My work at Yacimientos Petrolíferos Fiscales was very interesting, but I was not well treated. Otherwise, I would have stayed there. So I was very fortunate for mathematics that Calderon was not well treated at YPF. Okay, so let me describe a little bit Calderon's problem in detail. So Ohm's law, this is one of Maxwell's equations. In the case of electrostatics, is that the current is the inverse of the resistivity. The conductivity is the inverse of the resistivity times the change in the potential. So this is the current, and so if we have no sources or sinks of current, the divergence of the current is equal to 0. So this is the very simple second order PDE, and again, it's Maxwell equations in this particular case. And the conductivity can be isotropic, for instance, blood and so on, or anisotropic. For instance, in muscle tissue in the human body is very anisotropic. Muscle has a much higher conductivity in the longitudinal direction than the transversal direction. And that corresponds to the case of a matrix, which will be of interest to us. So now you have to decide what are all the possible measurements that you can make. What does it mean to be invisible? It means that whatever measurement you make, you cannot find out what is inside. So you pose the Dirichlet problem, you put the voltage potential at the boundary, and you measure the induced current flux, where mu is the unit outer normal. And the information, the current, induced current flux, is the normal component of the current, which is here. So Calderon's inverse problem, which is also called electrical impedance tomography, does the knowledge of this map determine the conductivity. So this encodes all the possible electrostatic measurements that you can make on the boundary. And in the mathematical literature, this is also called the Dirichlet-Neumann map, because this is Dirichlet data and this is Neumann data. So here comes the first hint of invisibility, what I said earlier about in the anisotropic case, the equation is invariant and the changes of coordinates. So can you recover? And the answer is no. If you make a change of variables, which is the identity at the boundary, so you make, for instance, a rotation inside, the boundary is fixed, and you consider what's called the push forward of the conductivity, which in terms of matrices is the matrix of the differential transpose. So this map composed with the conductivity, composed with differential divided by the terminal, composed with psi inverse. Then the measurements that you get is exactly the same as for the original conductivity gamma. And how do you see this? Again, it's the invariance of the equation and the changes of coordinates. You change the solution by this change of variables, and you will see that the new equation for V involves the push forward of the conductivity, and the information is the same. It's very easy to check. So why is this not invisibility already? You put gamma equal to 1. You take the push forward of conductivity 1 by any change of variables. And then you get a new conductivity that gives you the same, exactly the same measurement. But for invisibility, the important point is you want, in the region that you want to be cloaked, you want to make invisible, you have to put any conductivity. And this is, so you will be able to identify, this is not any conductivity, you put the push forward of 1 inside, so you will be able to identify what is inside. But it is getting close. And let me put the problem in geometric terms. For the people who are not familiar with geometry, you can just think of a domain with a positive definite symmetric matrix. And again, this is the Laplace-Beltrami operator, which is invariantly defined. So I want to write the equation I wrote before in invariant terms. So you have a harmonic function with boundary values f. The conductivity now, what's the connection with the conductivity? Is a familiar expression, is the square root of the determinant times the inverse of this metric G. So you can think of this as a matrix or a metric or Riemannian metric. And in coordinates, the measurements are given by the normal component of the derivative with respect to the metric. So this is the induced current flux that we saw before at the boundary. I'm just rewriting the same thing. And so in geometric terms, this is the conormal derivative of the solution. And again, there's a current flux, and the problem now can be put in geometric terms. Can you recover these metrics, or the Riemannian metric, from knowledge of the Dirichlet to Neumann map or the voltage to current map? Okay, it's a complete geometric problem, very interesting one. And to rephrase what I just said, the answer is no. You take any change of variable, which is the density of the boundary, and now you take the pull back of the metric. Conductivities and metrics are inverses of each other. See, the conductivity is the inverse of the metric. So metrics pull back and conductivity is pushed forward. And so this is exactly the same, I'm just rephrasing what I just said for the conductivity. And this is another idea. So the first point was that the equation is invariant the changes of coordinates. And so look, suppose you have a drum bell, an abstract manifold here, and this is the boundary where you're making the measurements. You're trying to identify the conductivity or the metric inside. Suppose you pinch the neck all the way, then you're not going to be able to say anything about this side of the drum bell. It's completely disconnected. You have disconnected where you're making the measurements to the region that you want to determine. You cannot determine anything, so this is invisible to any measurement that you have here, but you have created a singular metric here. You're pinching it all the way. So that's the idea. So how to do this in Euclidean space? This is just an abstract manifold. And this is the main idea of transformation optics. Very simple one. So here is Harry Potter. It's a fish now. They're not the fishes of Percy the Connie's talk yesterday. So we want to make this invisible, this blue fish here invisible. So what I'm going to, this is virtual space here, and this is physical space where this is actually happening. So what I'm going to do is contract this ball to this point, or expand this point to this ball, make that change of variables. So I'm going to take this and make it a ball here. So a point by this transformation corresponds to this ball here. Whatever is inside corresponds to a point. And you can see this transformation takes the standard Cartesian coordinates, which corresponds to the rays of light, curves them, warps them around the object in the way that we want. We want to bend light around the object and make this invisible. So we're going to take a transformation, and the problem is invariant the changes of coordinates that blows up this point to this ball. And why will this be invisible? Because this corresponds to a point in virtual space, and a point is invisible. You cannot see a point. There are many other objects that are invisible. For instance, a line, a curve. In more technical terms, any set of houses of dimension less or equal than 1 is going to be invisible. You can do the same type of thing. You can use other transformations. It's a very flexible method. We're going to see another application of this idea later on. And so this is the transformation. This is expands this point to this ball, or blows up this point to this ball, transformation F. And I can write it down. In this case, this is a change of variable, which is the density at the boundary. And now you just take the identity. This is what you want to mimic on the ball of radius 2. You push it forward by this map that we just built. In the annulus, in the region that you want to cloak here, you want to cloak this here. So this is the Harry Potter's cloak here. We want to see what is the conductivity here. You just push forward the identity, and you want to look at in terms of metrics. You consider the metric associated to that, and in spherical coordinates is anisotropic, it's a matrix in dimension 3. We're taking points where the sign is non-zero. But notice that at the boundary of the clock, when r is equal to 1, this is 0. So the eigenvalue vanishes to first order. So this is a singular conductivity. So r equal to 1, this vanishes. And then inside the clock, on the ball of radius 1, you can put an arbitrary, this is what we wanted, an arbitrary positive definite matrix or conductivity. Anything, you can clock anything inside, and the theorem is that you do. So the measurements that you make for this new conductivity, that this is in the clock of invisibility, and arbitrary inside is the same as conductivity 1. This, as I said before, this is very flexible method. Instead of a ball, you can take another shape. Or instead of trying to mimic the identity, you can try to mimic any other conductivity. You try to make it look like anything else. And the currents are this. This is what I mentioned, I drew before. The currents go around the object. And when you make the measurements out on this board or outside, it's exactly the same as conductivity 1. So this is the blueprint for the clock. We know exactly how the conductivity has to look like. You can write it down. And this applies, as I said earlier, to any equation that is invariant on the changes of coordinate. For instance, Helmholtz equation. Now you have non-zero frequency here. The physical interpretation is different. This corresponds to sound. It's acoustic clocking, but notice that this is exactly the same as before, but this is density now, anisotropic density. And this is the bulk modulus, and as before, the inverse of the matrix is exactly the same, and the theorem is that the boundary measurements for this is the same as the identity, because this equation is invariant the changes of coordinates. And in the physics literature, this was realized as also in these two papers as acoustic clocking. This is in 2 dimensions, and this is in higher dimensions. And so you can do many things with this idea of transformation. So I asked one of my female graduate students who she thought was the sexiest man, and she told me George Clooney. I don't know whether women here will agree with that. But so I can transform myself into George Clooney. This is a different device. It's not exactly what I mentioned before. And this is in a paper in Physical Review Letters. So the days of plastic surgery are counted. And you can do the same for Maxwell equations now. This was our goal for light. You want to do the same for light. So Maxwell equations are invariant the changes of coordinates, as I mentioned before. And so now we have the blueprint for invisibility. It's exactly the same as before. Epsilon equal to mu equal to the inverse of the matrix times square root determinant of G. And the theorem is that the boundary measurements for vacuum, for the identity, is the same as this new G tilde, these new electromagnetic parameters. Again, it's arbitrary inside in D. And we know exactly how the epsilon and the mu have to be in the clock of invisibility. There is a technical thing here that the Dirichlet-Neumann map is not what we had before, because Maxwell equations is a first order system. So you map, all the electromagnetic measurements are encoded in the following map. You send the tangential component of the electric field to the tangential component of the magnetic field. Okay, so let me describe very briefly some extensions and other work related to this, because this is very nice. It's perfect clocking. You can completely disconnect this region for where you're making the measurements. The problem is that the electromagnetic parameters are singular at the boundary of the cloak. That creates problems for practical problems. Can we create those materials? So there has been a lot of work in the mathematical literature and also in the physics literature about trying to have non-singular parameters. For instance, let me take this case, and the idea is very simple. You just, instead of taking the conductivity that we had before, or the elastic parameters, or the density, or whatever parameters that you have, you truncated it near the R tells you the distance to the boundary of the clock. So you truncate it, you make it what you knew had to be to have the clock, and then arbitrary afterwards. Here I put the 2 times the density, but can be an arbitrary. But now this conductivity is non-singular and anisotropic. So now we are in the real, this is not going to be singular, and so maybe easier to build. And the theorem in that case is that for this this is truncated conductivity from the one we had before approaches the Dirichlet-Neumann map for conductivity 1, which is what you're trying to mimic. And this is good enough. You even have rates of convergence depending on the situation, because you don't need to have perfect clocking, you can have an approximate clocking. And so there have been several proposals. This is the idea of truncation in these papers here. And has been other type of approaches, for instance, blowing up, instead of blowing up a point, blowing up a small ball and seeing what the limit is as the ball shrinks to a point. For instance, that was the approach taken in this paper of Kohn, Chen, Vogelius, and Weinstein. Has been very active field about approximate clocking in different situations. You can even do approximate clocking with isotropic materials by doing homogenization. I'm not going, since I'm running out of time, I'm not going to talk so much about this. And also do quantum clocking. So quantum clocking is also of interest at the very small. I want to mention a very famous speech of Richard Feynman. He said, what I want to talk about is the problem of manipulating and controlling things in a small scale. There is plenty of room at the bottom. This was, in some sense, the start of nanotechnology. He said that you can put in the pin of a needle all the information of the libraries in the world. And this was very controversial at that time, and very famous physicists had said that that was not possible, and he was proven wrong. But again, the ideas are very similar to what I had before. The metric is exactly the same, has a different interpretation, is effective mass, as this was done by Chang et al. It's again the same, the fact that this equation is invariant the changes of coordinates. So let me not describe that. So let me go to sensors. There is a problem with clocking. I mean, Harry Potter is completely cloaked, but he's also completely in the dark. They cannot see him, but he cannot see anything from the outside either. So there is a question of whether you can put a sensor inside the cloak in such a way that you can detect what's happening from outside. And this is based on approximate clocking. We cannot get perfect clocking, so a little bit of the wave penetrates. You cannot see it. So the question is whether you can have a magnifying glass that makes this wave much larger so you can see what's happening in the outside. And this is done, and technically you put what's called a roving condition. This is the clock here inside this board. Put a sensor, by changing this parameter alpha, you can magnify the wave that's coming in, and so you can detect what is outside. So let me tell you what happens in the sensor mode for particular sets of alphas. So the wave comes in, and then is magnified inside, so you can see what's coming from outside. Okay, so I don't have time for that. So let me now address the question of whether you can do this or not in practice. So we have the theory. We have a blueprint for invisibility. We know what the epsilon and the mu have to be. Can you actually do it in practice? And it's not so easy. It's because the mu, the magnetic permeability, is hard to adjust. Most materials have mu equal to 1. So this is in the subject of what's called metamaterials. It's a very active field in material science, and it was named one of the 10 insights of the decade by science, one of the, actually maybe the only one in physics or mathematics for that matter. Most of them were in biology, chemistry, and so on. So in the past decade, physicists and engineers pioneered new ways to guide and manipulate light. So this is the important thing. We know how to manipulate light in some sense. And what we have concentrated on is constructing clocks. So can you do it? So let me mention two examples of metamaterials. Metamaterials means beyond materials. So these are materials not found in nature. Of course, it will be invisible. You cannot find them in nature. Maybe dark matter or dark energy is just clock. So one example of a metamaterial, this is a little bit related, it's not clocking, it's related to clocking, is negative refractive index, which is also a lot of interest because you can, again, manipulate light to refract in a different direction. So this physicist, Veselago, an Ukrainian physicist in the late 60s, postulated that it might be possible to have negative refractive index. The materials that we know have positive refractive index, and when you're told in physics is that the index of refraction is positive. So if epsilon and mu are negative, you can take the square root, and then the minus sign will make sense. This is what Veselago said. And it was very controversial. In the physics literature, several people said that this was not possible. And then in 2000, David Smith and his group at that time in San Diego built the first material that had negative refractive index constructed, very cleverly constructed with these circuits in the form of C-shaped circuits that refract light in a completely different way. So this is the opposite direction of what you will expect for a regular or positive index of refraction. But this was done, and this is an important point, at microwave frequencies. Okay. Before, in the theory, the frequency did not play a role. This was valid for all frequencies in principle. I'm going to address that question in a minute. So this is just a simulation of what the negative refractive index will do. Is you will see you're throwing in a completely different direction that you normally see. Of course, water has positive index of refraction. And then this was a breakthrough by the group of Chang in Berkeley that constructed the negative index of refraction for visible light. The reason why the frequency plays a role is these materials that you need are built at the wavelengths or smaller than the wavelengths. So the higher the frequency, the smaller the wavelengths, and it's harder and harder to build these materials. So this you can see is a very small. But it was possible to do it for visible light. How about clocking, metamaterials for clocking? Will be able to buy a Harry Potter's clock in the store someday? I don't know, but however, for, again, microwave frequency, the same David Smith, now at Duke, using similar, or in fact, exactly the same type of circuits, these, they are called slit ring resonators. But the construction is different. He took layers of this, again, designed in such a way that the epsilon and the mu, we have a prescription, a theoretical prescription for the electromagnetic parameters. So he tried to approximate those as much as possible in these layers. So this is the cloak of invisibility, and here there was a cylinder of copper that was made invisible. And you can find the experiment in YouTube. So this corresponds to the picture I showed earlier of the waves coming in and then being deflected around the object, and whatever is in here is invisible. And there has been some progress, and you can for visible light. However, the jury is still out about that, and there is you can see reports all the time about experiments being done for visible light for cloaking. However, right now they are for very small objects. So another thing that you can try to do is what's called artificial black holes. It's the opposite. So a group of physicists proposed the opposite of what we just did. The light will go around, they're trying to trap light here, similar to a black hole, to create these artificial black holes. The idea is to try to do experiments with black holes in the laboratory. Of course, we cannot do experiments with black holes in nature. And here is where the main progress is going to come from, in my opinion, in terms of practical applications or constructions, is for acoustic cloaking. We saw before that it's also possible to cloak sound waves. So sound waves will go around an object and making this completely soundproof. You cannot hear anything from the outside, and that's what you would like for a concert hall, for instance. And recently, different Chang constructed an acoustic cloak just built with plastic and making holes in very specific places. So it's not a difficult material to build that will have that effect of having sound waves go around. So if I will have to bet what will be the first cloaking practical application, will be acoustic cloaking. So this was experiments done. Another possible experiment that has been done that is related to what I mentioned before, cloaking will be true for any equation that is invariant the changes of coordinates, is for linear surface waves that have been called tsunami cloaking. So you build in a very similar way to what we did before for electromagnetic cloaking. The water will go around the object, and when you observe it outside, it's like it went straight through. But this will be completely impenetrable by the water. And there have been some experiments done in the lab, not at the level of tsunami cloaking, of course. And the reason why this works is because the equation of surface waves is invariant the changes of coordinates. So let me finish by making another interesting connection with science fiction. This is wormholes. This is one of the potential predictions of general relativity that has not been found in nature. Of course, it has attracted a lot of attention because it will allow for time travel. So you can have a shortcut in a space-time if you can build these wormholes. So there is one of my favorite science fiction movies is Contact. We don't have a simulation we haven't found an electromagnetic wormhole, what it will be to go through a wormhole. Okay, so the question is, can you build electromagnetic wormholes? So the question is whether you can trick the electromagnetic waves to think that they are going through a handle instead of going straight through like in a cylinder. And this has been called Harry Potter's invisibility sleeve. So this is the situation. You have a cylinder here, and now we're going to build this by blowing up a line. Remember what I said, that lines are also invisible in dimension 3. Curves are invisible in dimension 3. So we blow up a line and we build this cylinder. We're going to make this part of the cylinder completely invisible. You're only going to see what's coming in and what's coming out. And you can encode, because we can put an arbitrary metric here, arbitrary electromagnetic parameter, we can encode what's coming out. So we are creating a secret connection between two different points in space. So these are ray tracing simulations. So in this part, this is completely invisible. The rays of light go around. But here inside, you can have many possible situations. The ray can wiggle around and can come back and be trapped and so on, because you can prescribe what is inside completely arbitrarily. And this is some rays tracing simulation with different metrics inside the cylinder. So at the end of the wormhole is a sphere, the other end is sort of an infinite chessboard under the blue sky. So you can see many different effects depending on the metric that you put inside. So what to do with a wormhole? Let me mention some potential applications that maybe the grandchildren of the young people here will see someday. Invisible optical cables. Optical cables function because there is a lot of reflection. Light is trapped inside. You have internal reflection. You can make those optical cables invisible. I'm not going to describe all the possible applications. For instance, you can have three-dimensional television. The cables are invisible in this room. You only have the input and the output. Of course, you can manipulate the output. You can have a virtual magnetic monopole. You put in a magnetic field and another magnetic field comes out all of a sudden. Maybe you will be able to use this for magnetic resonance imaging devices, because MRI, what's called magnetic resonance imaging, is one of the most powerful medical imaging techniques, but uses a very strong magnetic field. So you cannot use surgical instruments when you're an MRI at the same time. Maybe one possibility is to put the surgical instruments inside the wormhole to protect them from the magnetic field. An amusing application, this is not ours, is by these two authors, Watch Your Back. So you have bifocals. Half of your glass you can see in front, and the other half is attached to two electromagnetic wormholes, which are invisible, but you can see everything that's going on in your back. So you can watch your back that way. That might be useful sometime. So I'm asked the question many times whether cloaking will be possible someday or not. Well, it's very hard to predict, especially the future. But if Maxwell will be alive today, he will think that all these things that we're using, computers, cellular phones, et cetera, are magic. A lot of the modern technological applications will look like magic, even to a person that was born at the beginning of the 20th century. And also another quote, this is one of my favorite science fiction authors. Any sufficiently advanced technology is distinguished from magic. And I have been made throughout an analogy between general relativity and cloaking. So general relativity, you have Einstein's equations, and for electromagnetic waves, you have Maxwell equations. These are two giants of physics of the 19th and 20th century, and we have used transformations for cloaking. So there is in some sense a transformation from Einstein to Maxwell. So let me finish with that. Thank you.